So, hello again everyone. My name is Mathieu Stoffel. I work at EUPEX and I collaborated with EUPEX and Samuel from ECMWF to focus on the energy efficiency of one of the components of the IFS on gray superstructure chips. So basically, what are we going to talk about? I will start with a brief introduction of what is the IFS and more specifically EC-trans. And after that, we'll have two studies, each one in a section. The first one is an efficiency comparison of EC-trans on 3 different architectures. And the goal here, the motivation, was to get some insight on the most utile hardware targets for EC-trans. In the last section, I will focus a bit more on static GPU frequency scaling for EC-trans. And the goal is to see if we can leverage some efficiency improvements for EC-trans with frequency scaling when executing on GPUs. So, what is the IFS? It stands for Integrated Forecasting System, and basically it aims at forecasting weather-related physical quantities, such as temperature, pressure, and stuff like that, over Europe on a 15-day timescale. The forecasts they build are highly precise. When they say it will rain, take an umbrella, basically. And they have a high resolution. So one side of the cell of the computational grid is between 8 and 9 kilometers. If we translate that into images, they have data assimilation facilities, such as weather station. They run complex numerical models on supercomputing infrastructures to build weather forecasts. And we will focus a bit more on one of their components of the IFS, which is called EC-trans. So I will quote Samuel on that. EC-trans is a high-performance numerical library for transforming meteorological fields between global grid point space and a spectral representation. So I hope you get that, because the guy who could explain it is not here with me today. So if you have any question, I will direct you to him. One important note here is that EC-trans was closed source until 2022, where it was open sourced. And from that, they even built a benchmark we used quite a lot. Just a quick joke on that. I am only 2 years older than EC-trans, so you are looking at more than 30 years of development and optimization for the code. One final remark, because I am going to use this acronym quite a lot. The acronym is TCO, and it won't stand for the total cost of ownership. It's the truncation cubic octahedral. So basically, that's an input parameter for EC-trans. And with that, you can set the overall resolution of the computational grid. So basically, the higher the TCO, the larger the problem size. I will use that to do workload scaling in the experiment. Just as a reference, at ECMWF for the forecast, they are using a TCO equal to 1279. Okay, so the first study. The goal is to see what is the best architecture to execute EC-trans between 3 of them. The first one is an x86 node. So it's a state-of-the-art Intel-based compute node with 2 Intel Granite Rapids CPUs. VSB, so the entity Ondra belongs to, just bought some of them. And the other one is is a node based on Grace Hopper 200 modules. So I will use this node to be sometimes an Arch64 node and sometimes a GPU node. So when I will be referring to Arch64 nodes in the remaining of the presentation, it means that I use only the Grace part of the nodes. Okay, so for this comparison, I did a single node study with the same experimental parameters on the 3 different architectures. The goal was to monitor performance and efficiency for EC-trans. So I scaled the size of the workload by increasing the TCO from 100 to 1000. Why 1000? Because that's the biggest size of an input dataset that fits the memory of the GPUs. So I could not scale higher on one single node with GPUs. On top of that, I monitored the power consumption out of band with a 1 Hertz frequency. So every 1 second, we have 1 power sample for the power consumption of the full node. And that's done thanks to Argos, which was presented by Thomas earlier in the software stack. EC-trans reports a performance metric which is called the duration in milliseconds of the inverse direct transform. So basically, we have the execution time of this transform as a metric. The shorter the execution time, the better. Okay, so the first study on x86 node. Basically, you have the evolution of the execution time as a function of the TCO. Once again, the higher the TCO, the bigger the impute dataset. The point we are going to use here for our comparison is the TCO equal 1000 because that's the one that's the closest from their reference production runs. So I have numbers here. I will come back to them later for performance and for power consumption when I will compare the three architectures. I did the same thing on using only the CPU part of the Grace hoppers. And here the power consumption is only the power consumption of the full node minus the power consumption of the 4 GPUs. Everything was monitored out of band, so basically no perturbation on the workload. And I have the power consumption of everything but the GPUs, just so that it is clear. Once again, I have numbers, and I will come back to them later. And finally, I did the same thing with the GPUs. Here it was offloaded to the GPUs with OpenACC. There is also an OpenMP version of the offloading, but it does not work on GH200 yet, just so that you know. I have numbers for the performance, but I had a little issue with the power consumption. So let's focus on that. Here, for the run with TCO equal 1000, you have the evolution of the power consumption and of the GPU usage rates of the 4 GPUs during the run. Here, you can see that there is kind of an imbalance between the GPUs, but that's okay, that's kind of by design. However, we have a limited usage rate of about 65%, which translates into kind of a low power consumption, half of what we could expect for HPL, for instance, the GPU. And that is a problem, because usually when you have this kind of usage rate and of power consumption, it means the application is not using the GPUs efficiently. Here, when we dig up a bit into the source code, we saw that they were allocating the memory on the GPUs and transferring data from the CPUs to the GPUs within the main computational loop, because they are precisely timing what happens in this loop, and that's their performance metric. Since they are monitoring all that with Nsight, which has a graphical interface, they can just extract the kernels and see what happens for the kernels. So the fact that the memory allocations are not done in bulk before the main computational loop translates into all those low GPU usage rates. And the main issue for my work here is that I cannot use the full node power consumption of the benchmark to have kind of a representation of what will happen with EC-trans in a production context. Because in production, you won't have this memory allocation within the main computational loop. So I had to work around the issue. And to do that, I decided to use a surrogate application. Basically, I want to build the worst case scenario. I want to be able to say EC-trans won't consume much more than that kind of power when executing in a production environment. And to build that worst case scenario, I used GPU burn. So that's a small benchmark you can easily find on GitHub, which will translate into a 100% usage rate and with a very high and steady power consumption. It is very, but very, very unlikely that an application will consume more power than GPU burn when executing on the GPUs. So with that, I have kind of my worst case scenario. I can say EC-trans won't consume more than, and you have the number there, it's almost 4 kilowatts, and that's our worst case scenario. If I inject that into the result I had for the GPU, and that I make the comparison, several things appears. Even in the worst case scenario, the execution on GPUs is more than 30% more efficient than on the CPUs. So that's quite significant because that's worst case scenario. On top of that, we have at least a 4 times speed up between CPU-centric nodes and GPU nodes. We are 4 times better in terms of performance on the GPU. So here, GPU seems to be the best target for EC-trans in a future production context. One additional remark here before going to the next study, even when you consider the density point of view, that means the number of performance per, I would say, square meters of rack and of computing facilities, GPU is better because you have one GPU per one U when you have 3 CPU nodes per one U usually, and we have a 4 times speed up. So you still have more performance and more efficiency in the point of view of density. Okay, so that was the first study, and without any condition, I go to the next one. This one focuses on GPU frequency scaling on EC trans. So why are we interested in GPU frequency scaling? Just as Monja presented in the previous talk, it's a way to decrease the power consumption of the GPUs. However, it might have a big impact on the performance of the application if not done at the proper timing. So before trying to be as refined as the approach of Merrick, I wanted to see if a static GPU frequency, other than the nominal one, could yield better efficiency. And so that's precisely the goal here. See if there is a better static frequency than the nominal one. So how to evaluate that? Well, that's quite simple. I selected the subset of the GPU frequencies because there's quite a lot, and I didn't want to burn too much GPU hours. So I selected the subset 900 MHz to 1980 MHz. That's the reference or nominal frequency here, with 90 MHz there. And for a TCU of 1000, I executed EC trans while monitoring the power consumption to see if there was one frequency that was better than the others. Since we still have the problem of not being able to make projection or simulation for EC trans in a production context, I also used GPU burn to build what I call an abacus, so something that says for this frequency, you will consume at most that much power. So here are the results obtained with GPU burn. So basically, the same sequence was executed 3 times, 30 seconds of what I call between quote idleness, which is in the fact very low activity, then 5 minutes of executing GPU burn, and after that 30 more seconds of idleness. All the gray bars are the average power consumption when we are executing GPU burn. All the red dots are the power sample. So each point is one power sample during the execution of the whole sequence. And so you have the idleness here, all the samples taken during the 2 times 30 seconds, and here at the top on the bar, you have the power samples during the execution of GPU burn. And so that is our abacus. We can say, for instance, for the frequency 1620, we will consume at most something like 3600 watts. That's the worst case scenario. We have one thing which is interesting here. That's the plateau here. It's not supposed to happen. Basically, if you go faster, so a higher frequency, you consume more power. So we are not supposed to have a plateau here. The best hypothesis here is that on top of the module power cap and the GPU power cap, you can have a system power cap on this node particularly, just to ensure that even at the node level, you are not consuming too much power. And it is hard-coded into the BIOS, into the firmware of the blade to 4 kilowatts. There is a slight difference here that I think could be explained by the power transformation, which is not accounted here. So basically, here what you see is that for the single GPU node I used, the power consumption required to sustain a higher frequency by the GPUs is not reachable on this node. So basically, it means that effectively, the node cannot sustain a higher frequency than 1710 MHz when fully loaded on this precise node. And something I want to have a few words about is that this value here will depend on the specific node, because each GPU, depending on its etching, will not have the same power consumption for a given frequency. So you can have nodes which are better to reach higher frequencies and others which are not. And that's something to keep in mind, and there are lots of interesting discussion about that we can have off the presentation if you want.
If you will have a workload of a different arithmetic intensity, it may reach higher and be beneficial from these frequencies.
Exactly. you are totally right here. And just for the, well, I have a bit of time, so. We are using one of the version of the twin version of the blade, which is in Jupyter. The blade in Jupyter has a system power cap of 600 watts per GPU. So why this? To have double the density. We have 2 GPU nodes per blade. And that is based on the etching of the GPUs. The GPUs used in the max quantity version are in lower bins in terms of efficiency when solved by NVIDIA compared to the other one we use in the max P blade. So here we are supposed to have the best in terms of efficiency of the GPUs solved by NVIDIA when doing this kind of blade. Well, that was just for the, I would say, the little digression. Okay, so moving back from GPU burn to EC trends. So here it is EC trends benchmark once again. So you can see that the power consumption is not at all near 4 kilowatts. Still, we have this plateau for the higher frequencies. That's because the load for those frequencies is enough to reach this plateau. But the 2 other frequencies which were in the plateaus are not here. So that's precisely what Andrea said. If you are not sustaining a full GPU load, you might reach higher frequencies, but under an heavy load, the maximum reachable frequencies will be lower. On the thing we can also notice, there is kind of a sweet spot for efficiency because performances are quite stable even with lower frequencies when the power consumption decreases. So here there might be an efficiency sweet spot. And if we scale down the frequency too much, the performance degradation just skyrockets. So we should not do that if we are interested in maintaining a high level of performance. If we translate that into efficiency, we get this graph. So basically, it's efficiency in red and performance in blue relative to the nominal frequencies, so the bars on the right. Basically, here, for instance, for this frequency, we have almost 10% more efficiency when comparing to the nominal frequency. But we also have more than 10% performance degradation. So that's quite bad, and that's why we can spot our sweet spot that we mentioned previously. For those 2 frequencies, we have efficiency gain, more than 5% at half the cost in terms of performance. So just with a static frequency change, we can leverage quite significantly more efficiency at a low cost on performance. And that's quite of a nice result. And the last slide, the last 2 slides, are about what happens for production EC trends. So once again, I used the abacus I built with GPU burn, and I say, what if EC trends is consuming the maximum amount of power we can imagine? The graph is essentially the same, but we can see potential for way bigger efficiency gain. That's because when you perform frequency scaling, you have the benefit only when the core are active. So basically, if you increase the usage rate, the efficiency gain potential is higher. It could reach 38% of efficiency gain at a big cost of performance, but here you can be quite efficient if what you want is the number of performance per consumed watt. We still have a sweet spot, but slightly translated to the left of the graph, and here we can reach more than 8.5% of efficiency gain for less than 4% performance. So that's an also quite nice trade-off, I think. And on that positive note, I will go to the conclusion. So in the first section, we saw that we had better performance and better efficiency on the GPU. So that's most likely the best target for EC trends. In the second study, the last section, we saw that the maximum GPU frequency was not always the best from the efficiency point of view, and we can have quite nice sweet spots, even with static frequencies, to have more efficiency at a low cost performance. That's all for me. I thank you for your attention, and if you have any question, now is the time.
Sorry, only a general remark,
yes?
Maybe not for this presentation, but in general. There is an attempt, maybe before, from a presentation from from the work package 5 guy. I understood that there is an attempt to couple performance profiling tools like Scorpio Scalaska with performance power model. So in particular for easy transfer, maybe better for IFS, I would say that this is as there are complex application, complex execution pattern, this should be useful also because otherwise not everything is flat in the direction of
I understand that completely. The tool I'm working on in the context of EUPEX is called DPO, for Dynamic Power Optimizer. And we are only supporting CPUs as of now. And this study was kind of to pave the way for the support of GPUs. And we are totally agnostic of the application. That was why it was in the motivation. We don't want to know anything about the application. We don't want to annotate it. We don't want to recompile it. The goal is user adoption because we have a coupling with Slurm, but the user, when he starts his job, he can just say --DPO equal yes, and everything runs directly with the optimizer. That's the goal. So that's why we are complementary of other approaches, such as the one you mentioned, or the work of Merrick and Countdown, which goes a bit deeper sometimes into the application. It's to have a tool for the user who wants to optimize his application, and a tool for the user who do not want to do that, or for the system administrator who said, hey, perhaps I will try to leverage some energy efficiency without expecting the user to do anything. So that's why I think that's complementary, and that can be both including into the, I would say, the work package and also the stack. They are not mutually exclusive, I think, not at all.
Sorry for skipping in, but under the POP Center of Excellence, we did perform energy efficiency analysis of the application, no optimization, so only the evaluation, performance assessment and energy efficiency.
Couple.
Yeah, sure. There are opportunities for improvement.
It's not realistic.
Yeah.
It's not an easy job, but when there is a will, there is a path.
Yeah, I will present something about Scorpio's outpost.
Yes.
I know very well.
Looking forward to it.
Thank you. Really nice presentation. And I mean, this is a single node study, but this number is 5% must be multiplied for the entire facility, maybe. And so the quantitative numbers are really intense. You did the study using the average power. Maybe, I mean, considering energy, the interval over the time could allow us to give the accounting in energy.
Yes.
And maybe regarding power, it's interesting, the peak power. Because the power at the very end is the stress on the electrical components of our facility. So reducing the average power consumption reduces the probability of failure. So it contributes to the general efficiency of the data center. So it's really interesting. And then I have two questions, but
yes.
Maybe a technical details. You force 5 minutes of execution using GPU burn, or I mean, if the automatic power capping or module capping enters, the duration is reduced. This is the first. And the second is about the nominal frequency. You ask for a frequency, and it seems that the module is not able to reach the frequency.
Requested.
Can you measure the actual frequency out of band?
Okay, so out of band, it's a bit tricky. As of today, for this blade, it will be a challenge.
Okay. Because
I have thought of a way, but I'm not even sure it could work. So it would be indirect. It would be estimation of the actual frequency. So we can discuss that because it's a quite hard topic, and I'm not 100% confident it would work. So we can discuss that, I would say, offline if you want to. But to answer simply the question, no, we cannot monitor it out of band.
Okay, thank you.
For your first question, it was regarding GPU burn. The run was, I asked GPU burn, you can specify how long you want it to run.
5 minutes.
So that's why I used 5 minutes, because that was kind of the same execution time as the EC trans benchmark. And that's not too short to be able to properly hit the components. That's something important when you are doing power measurements. And I am not sure I understood with the question, the part of your question with the relation to the system power cap.
I mean, if the system power cap intervene,
Okay.
the frequency is altered.
Yes.
So this alter your time to solution, or the time to solution is still, I mean,
No.
5 minutes.
It's still 5 minutes.
Ah.
It is for GPU burn, because we can. It's an input parameter of the application.
Yeah.
It is not altered. But
Okay.
you are right, for an application which is set to run, for instance, 200 iterations and not 200 seconds, if you put a system power cap in place, you will have a dilatation of this execution time, because, well, if it reaches the power cap. If it does
Yeah,
not,
good.
it should be
But it's a
transparent.
synthetic benchmark, as you said. Thank you very much.
You're welcome. I am 1 minute over my my question time, so I think.
Yeah, just
Oh, yeah.
out of band grades of power monitoring. So is it the EUPEX SDV?
Yes.
Is it available for everyone?
Yes.
Can you share how to?
Of
So
course.
IPMI or
Redfish.
Redfish reading.
Redfish, and you have also the power consumption of each GPU individually,
Okay.
and of the module, I think.
Yeah.
Also.
Okay. Is it also the same in the Jupiter?
It should be.
Okay. Good to know.
I haven't had max Q, because the two versions of the node I was mentioning are max P for max performance and max Q for max quantity. Here in the SDV we have max performance, in Jupyter it's max quantity. So I have not worked with a max quantity yet. But it should be the same.
Yeah. Okay. Thanks.
Just send me an email.